I bought some cheap lights off Amazon, but it's never as easy as that, is it? Come with me on a journey of failed lights and reverse engineering. Okay, so we have our lights, dirt cheap off of Amazon, and they advertise 40 watts of light and had pretty good reviews, although some of the reviews were quite telling in that people were talking about burnt out LEDs and hot drivers and so on and so forth. So I sort of bought them knowing that this was probably going to be a journey. First, when playing with these when they arrived, I was seeing how bright they were in the shop, sort of holding them up and playing with them and switching them on and off really quickly and all of that. And the first one went pop. So now that I had one dead LED strip, I could take it apart and see what's inside. And inside is a LED control board, and it looks like that. It has two sections. It has an AC input section and then two DC to DC power converters. At first glance, this looks like an isolated switcher because we have transformer looking parts, but in fact on closer inspection these transformer parts labeled T1 and T2 are in fact just inductors. So this is a non-isolated DC to DC switcher. The circuit board is connected to the end cap by some very disappointing crimps into that end cap. And I suspect this was our point of failure in that these crimps just wiggle and buzz, and you can get them to make buzzing sounds while the light's on. So I suspect what happened was while I was wiggling the light, we got a whole bunch of interruptions and noise from these connections. The circuit board got confused and overcurrented the lights. So now we have that. Let's switch over to a different view and go through the circuitry. We'll start with the AC input circuitry and move on to the circuitry for each of these DC to DCs. Then we'll compare to datasheet recommended values and figure out a set of changes we can make to our lights to make them last longer. We have AC line and neutral coming in, a mauve safety capacitor going to two fusible resistors. Each one leads to a bridge rectifier whose output goes to each individual switching circuit, and they share a common DC ground. Let's move on to the schematic of each of the DC to DC converters. So here's our schematic for the board. I started looking on DigiKey for switching DC to DC high voltage converter chips and indeed found something extremely similar. This part here, it doesn't match, none of these part names or numbers match, but it looks like this is a fairly common architecture. I will get into the typical applications of this chip in a moment. So here's our schematic. We have our DC in with our 0.1 mic filter cap. We have it coming to 4 pins on the SO8 that is on the board. All of these drain, DDDD. And then from there, we have a DC to DC set up on the right-hand side here, coming from the source of the pin out through two resistors which set the current, an inductor, a output filter capacitor with a little bleed resistor on it. And then this goes out, and this actually joins up with the other circuit on there with a diode OR coming into the LED string, the 72 volt LED string. What else do we have? We have a feedback voltage regulating resistor coming to this M pin. M apparently stands for multifunction. This pin is used for a few things. This circuit is quite interesting in that when I was sketching this out, I kept looking for the ground. Like, where is the ground for this chip? And there is no ground for this chip. And what it turns out after reading through our data sheet, the chip makes its own power supply using what's called the bypass pin and 0.1. In this, on the board, we have a 0.1 microfarad capacitor. And while this chip is switching, depending on what point it is in the cycle, it will be able to charge this capacitor and create I believe, a rail just below this input voltage here for it to switch its transistor or MOSFET that's in here. During the on switching time of this chip, the drain will be connected to source. Current will flow into this inductor and start putting power current through the LED. As that current ramps up, the resistors will signal via the feedback pin that you've hit your maximum current, and this guy will cycle off. These switch at about 20 kilohertz or higher, and that way you can't hear the switching frequency. If there is an LED fault, if the LEDs go open for whatever reason, the maximum voltage to the LEDs will be limited by this feedback. Or if you don't reach your turn-off current before you reach your compliance voltage, this circuit will turn off the switch. So I worked through this data sheet, and we have a very similar, on page 3, we have a very similar looking schematic. The two things I've noticed here, they have a lot of input capacitance, and in fact they recommend that you should have 2 microfarads per watt, and their bypass capacitor is 4.7 microfarads, and it's just a 10 volt. The bypass capacitor does not get that much voltage on it. In comparison, our circuit has a 0.1 mic input capacitor, a 1 mic bypass capacitor at 50 volts, which is, I think, it's just a generic electrolytic capacitor. And otherwise, we're looking pretty good. They have a little bit more output capacitance than we do, but that's fine. Let's see what it means to have a 0.1 mic capacitor on the DC input after the bridge rectifier compared to a 47 microfarad capacitor on the reference design. The input to our bridge rectifier is AC. The output of our bridge rectifier is half sine 120 hertz bumps. And when we add a filter capacitor to that, we would get something that resembles a true DC circuit with some ripple on it. This is the sort of voltage we are more likely to see with a 47 microfarad capacitor, and this is the voltage we are more likely to see with a 0.1 mic capacitor. You'll see that the voltage goes to ground, or very close to ground, 120 times a second. Now, remembering what this switching circuit is doing, it is a 20 kilohertz or higher switcher. Anytime that input voltage is higher than 72 volts of the LEDs, it is turning on and switching. So I had initially drawn this as, oh, it's switching all the way through here, but it's not. It's actually, there would be a 72 volt line somewhere around here that it actually has enough voltage to run the LEDs. So it's actually only switching in this region here and then in this region here. And 120 times a second, it is turning off. This seems like not great operation. In comparison, the DC voltage with the 47 microfarad capacitor is always above 72 volts and always able to send voltage and current to the LEDs the entire time. And so we have constant operation where the chip is switching and charging that DC output capacitor all the time. So based on these discoveries and the schematic, I think we have some changes we can make. So let's look at our changes with an original board and a modified board. We have removed the 0.1 mic input capacitor and replaced it with a 47 mic 250 volt cap. We have removed our 1 mic filter cap and soldered on a 4.7 mic ceramic. We have removed the 1R6 current sense resistor, and we have changed our feedback resistor as well. This board can now only output 72 volts compared to 103 on the original. So that's about it. There were some things I wanted to capture in the video that I wasn't able to, such as final component values and some details on the schematic. That will be in the description below, but thanks for watching.